Swayam Prabha. Digital India. Educated India.
Welcome back, everybody. Here's your slew of reactions here. We got a wheel going for you. All of the reactions that we just talked about are pretty much on here in some form or other. And we're going to see what the outcome is for this molecule. This is an asymmetric molecule, and it's a cyclopentene, and that's ethyl cyclopentene. So let's see what ethyl cyclopentene is going to do with all of these reagents. Let's start at 1 o'clock and go around the clock, shall we? Let's look at BH3. Let's look at what this is going to do. I put the B in a different color just to show that that's your electrophile. So your BH3 is going to sit right on top or bottom, and the hydrogen is going to go to the most substituted carbon, and the boron is going to go to the less substituted carbon. Remember, we talked about the steric effects and how the crowded side wants to go to the side where it's less crowded. So it's basically sterics, and I'm going to draw an intermediate, and then I'm going to draw the two products for each one as much as possible. All right. So in here you have a transition state, and it's concerted, and you would have, let's say your BH3 came in from below. You're going to break that pi bond, and you are going to catch that boron and deliver that hydrogen onto the most substituted carbon, exactly the opposite of Markovnikov. So that's anti-Markovnikov. Here you can have two R groups or hydrogens. If you put R groups, your selectivity would be more, your regioselectivity would be much higher. And now you'll have this plus the one on top, so I'll put just plus minus, and you would have, after everything's broken, an intermediate where you'll have solid lines to this. So your intermediate here is going to then have attack from below and above. I've only shown one of them, and I'll just put plus minus to show that there is another one. And then you're going to oxidize with this. Your oxygen goes on the boron, then there is a migration, and then you'll form the borate, and then you would hydrolyze it. And you would get two compounds here that have boron on the bottom and top. And when that gets oxidized, you are going to put your hydroxyl down. And then we'll also have BH addition on top. And so I'll write the other counterpart to this, which is going to push that ethyl group down. And the hydrogen and the hydroxyl will always be on the same side. Hydrogen will be on the most substituted carbon, which would make it an anti-Markovnikov addition, and the hydroxyl would be on the same side as the hydrogen, which would make it syn stereospecific. In this case, they are both enantiomers, 1-to-1 raceme. This is your major. And your minor product can be the hydrogen and the hydroxyl switched. So that would be your minor product, and you may have others. All right, let's look at the second one, bromine and bromine. So this bromine would be a positive, and that would become your electrophile that attacks the nucleophilic pi bond. In all of these reactions, the first step would be the pi bond attacking an electrophile. And I've tried to put those electrophiles in green. So once you get the electrophile on here, we will get an intermediate. Again, this is going to have bromine on top and bromine at the bottom. And then the bromine is going to attack over here and move this over. You could also put the bromonium at the bottom and have the bromine attack from the top. Both of those are possible. I'm just showing you one scenario here. And that is going to give you opposite sides of bromine addition, bromine here and here. Plus, you are going to get your bromide up addition and swinging this down. And even here, this is going to be a mirror image of this. And it is anti-addition, and it is non-regio specific. You would get a 1-to-1 enantiomeric raceme. You are not really going to get any syn addition here. Let's look at this same thing, but here instead of a aprotic solvent, you have a protic solvent, any alcohol. Same deal as before. The first step is where you have your bromonium form, and it can form above or below. And then your bromide can attack, and then your solvent, because it's a lot more than the amount of bromide here, can attack from below. And their solvent is very specific about where it wants to attack. Let's say this is your solvent, it's just an ethanol. It's going to attack on the more substituted carbon just because you want to form a carbocation that's supported by more R groups. So this is regiospecific. Now you could form the bromide below, and the ethanol can attack from above. So you would have then a mixture where you would have your ethanol go down, and then it gets deprotonated, and therefore it pushes the ethyl group up, and the bromine would roll over. And so you would get a Br and oxygen on opposite sides. It's anti, but it is regioselective. Your minor product could be your oxygen here and your bromide here. So this is your Markovnikov product, and you could have the bromide down and attack of ethanol from above, but it's always going to be on the carbon that is more substituted. And in this case, if your bromide's below, it's going to roll down below. Now these two are also enantiomers, so you'll get a 1-to-1 enantiomeric raceme. Therefore, your major would be this. Your minor, as I said before, would be your anti-Markovnikov product. Let's look at this. Chlorine and acetic acid. It wasn't one of the mechanisms that we did. However, it's going to be very similar, mainly because this is an oxygen, and it can act like this oxygen or this oxygen. just nucleophilic. I'm just putting it for good measure just to show you that chlorine can also do the same thing as bromine. And I haven't really talked about iodine. When you add iodine like this, it's going to collapse and really go back to solid iodine. So we don't typically do this with iodine. It's typically with bromine and chlorine. Now acetic acid is protic, and protic solvents are going to ionizing, and therefore your bond is going to sever here to have a tertiary carbocation more than a secondary. So this is also very regioselective, just like this, and you would get the same thing as before, except that you are now going to have an acetic acid instead of a alcohol, and they would be on the opposite side, and after deprotonation you would get an OAC or an acetyl group here. Plus you would get chlorine going below, but the acetic acid will still attack on the most substituted carbon, the acetic acid or acetate above and chlorine below. So you can see these are also a 1-to-1 enantiomeric mix. What happens when you have something like this, a peroxide? If you have it in anhydrous dichloromethane, that's really important. You really have to distill that maybe a couple of times to make sure there's no water in there. And then if you go over here and you put your epoxide in, your epoxide can go above or below. And I'm going to put this oxygen in a pink color just to show you, even though that's the electrophilic oxygen, above or below. Now this is also going to be a mirror image, and you would get a 1-to-1 enantiomeric mixture. There is really no regioselectivity. It's syn stereospecific. Let's move on to this one. You have the same thing, but instead of a aprotic solvent, after you form your MCPBA epoxide, then you're going to open it up with some protic solvent, alcohol or water. Since we used alcohol, acetic acid, and so on, we are going to use just water here. You're going to have the epoxide form on top or bottom, and again I'm going to use a pink color for that. And then you're going to have attack of water on top or bottom. So let's say this was your intermediate. You can have attack of water and that's going to be very specific. It's going to attack at the most substituted carbon. So that is always going to give you a regioselective preference for having that protic solvent attack at the most substituted carbon. So you have regioselectivity here. So if this is up, then your water is going to go down, and then it gets deprotonated and becomes hydroxyl, and then this would get protonated and become a hydroxyl. So it's a diol, but it's going to be anti. And you can have the epoxide form below and have the water still attack at the same most substituted position. And so when your water attacks over here and gets deprotonated, your hydroxyl here is going to swing down and get protonated. And in this case, you can see they are mirror images. So again, enantiomers, 1-to-1. Let's look at what happens with MCPBA in an anionic environment or a basic environment. So here you're going to get the same epoxide forming with MCPBA and dichloromethane as your solvent, and you can form it above or below. Let's say you form it above. I'm only showing one. And your RONA can attack here mostly because it's an anion, it's going to do an SN2 type. There is no cation formation, so why does it want to get into this crowded place? It's not going to go there. It's going to get to the place where it's got a lot more space to do what it wants to do, which is basically get into the ring. So let's say I have a, that's going to go over here and roll over oxygen, make way for your new friend. So over here you're going to have your oxygen up and your incoming group down because it's anti-attack. Anti, 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 anti. All of these are anti-stereospecific. This is syn-stereospecific. This is going to go up. And then after you do this, then you're going to do acid workup like you would do, and you would get a hydroxyl over here. Plus you could form the epoxide down, but your anion still going to attack at the same place because it wants to have less steric to go do what it wants. So your oxygen anion is going to go above and roll over that epoxide down, and you would get your hydroxyl on protonation. Again, these two are going to be enantiomers, 1-to-1, raceme. Let's move on to this one, mercuric acetate. So all of these that you have a triangle for, if you would notice, have initial syn stereospecificity, which is why I kind of grouped all of these together. All of these form an initial triangle. So here too you would have an initial triangle with the mercury. And I'm going to draw that in pink. Then you're going to have hydrolysis, and then you would have hydrolysis over here. In this case, you won't have any migration or rearrangement just because you're going to form the tertiary carbocation, and then your sodium borohydride would eliminate this. So you would have a alcohol here, and the alcohol is going to go over here, OH. Now should I draw the other one too from attack from below? Well, this is achiral, so why even bother? All right, let's look at something where we don't have a syn. Let's look at this, where we have a HX. So your double bond is going to then get pulled up by the electrophile here, and you'll get a positive carbocation. So here your hydrogen would go to the carbon that's got more hydrogen. So we had a hydrogen here, and that's where your hydrogen from the acid would end up. Then you would have a positive carbocation here that's then going to be attacked by the X minus. So your X minus can go above and below. And do you think we want to write both of them? Well, let's see, I'll write both of them and then you can decide for yourself whether that was necessary or not. And we can choose any one of this. Let's say I'm putting in HI. So you would get iodine here. and then the hydrogen that you added would be here. And this is achiral, so it really doesn't matter whether you put it up or down, but I'm just going to write this here and say they're both the same. All right, so this is what would happen if you had an acid addition, acid with a hydrohalogen. Now, if you have your acid as H2SO4, you would get H plus and HSO4 minus. HSO4 minus is not a nucleophile. Water is going to be a nucleophile. So just like here, once you get a carbocation, water is going to attack it. That's the only difference between these two mechanisms. So if you have water attacking that, you're forming a carbocation. In this case, since you're forming a tertiary carbocation, you don't have to worry about rearrangement. You already got the best guy you could in the house. So now you move on and you attack with water. And does it really matter whether it attacks from above or below? Which it's going to do 50% up and 50% down, because this is a p orbital and this is sp2. So therefore you would get 50% up and 50% down, and then you would get deprotonation. Should you write the other one also? Let's see. Is this different from this? What do you think? The exact same thing. If I take this and just topple it over 180 degrees, put it on top, it's going to superimpose. So they are both the same. So therefore there's only one product here. This is equal to this. Hydrogen platinum, and again this we said it's going to go up or down. Let's write both of the products over that for that. So here is your hydrogen, and they can both be above. Should I write the other one? Is it necessary? Well, let's do it just for good measure and see if it was really worth your time. This goes up and your hydrogen's down. This is just ethyl cyclopentane. You can take this and you can put it on top of this and it's going to superimpose. So this is the same as this, no difference. All right, so here we go. These are again syn. O3 DMS, we talked about O3 going on top syn. Then it kind of scrambles, becomes a creepy intermediate. Then it forms the malosonide, then it forms the ozonide, and then it gives you a broken sigma. So you don't have a sigma, but you do have, in the presence of DMS, 2 oxygens on either side. I'm going to write this in pink just because it's hard to see the green against the yellow. So this kind of opens up and you're going to get just a long chain. So there's going to be 7 carbons there, and you would get a ketone here, and then you're going to get an aldehyde here. And that's really the major product. I mean, it's not 100% for ozonolysis typically, but that would be your product. Let's look at KMNO4, sodium hydroxide, cold. Okay, cold is really important. If you heat this up, it's going to chew up this entire molecule, give you carboxylic acid and ketones, something like this, but with a carboxylic acid. But if you keep it cold, almost close to freezing, then you're going to get hydroxide adding on the same side zin. Same side zin is going to give you, well, let's say 1 product or 2 product. This is a hydroxyl. Now you can also draw this with wedges and dashes, but I think this is a little bit more obvious for you to see. So I'm drawing these Hayward projections, and here you have your hydroxyl coming out like down. What do you think? Are they the same? Are they mirror images? If you flip it over, it's not going to superimpose. So these are now enantiomers, 1-to-1. All right. One more here, OSO4. So the osmium tetroxide is going to jump on that pi bond and hang on to that monkey bar. And then it's pretty much very similar to what you have here. You would have the osmium tetroxide hanging on to the alkene, and then NaHSO3 then hydrolyzes that, and you are going to get both the OHs on the same side. So KMnO4 cold and osmium tetroxide, like close cousins, they do pretty much have the same type of mechanism and same outcome, where you have hydroxylus down or hydroxylus both up. So here's down, down, and here's up, up, and this is a syn-diol, all right? And so therefore you are going to get a mirror image here. So this is enantiomer 1:1. Raceme. All right, so let's look at the stereospecificity. Stereospecificity, BH goes right on top, plunk. So that's a syn. So here you're going to have a bromine come in on the top as an initial syn addition, but the overall addition is anti. Same here, bromine as an initial syn addition, but the overall addition is anti. This is going to be an anti-addition as well. Overall addition is an anti. This one is just very specific, either one side or the opposite side, not both sides. So that is definitely a syn. This one is a syn followed by an anti. So I would just put S and then A. This one is the same, syn followed by anti. Now over here, this is also a syn followed by anti. I know it all looks like we got a lot of South Africa here, SA, but it's actually just syn followed by anti. Now over here, there is really no syn or anti-attack. You form a carbocation and then you attack with your iodide. So this is non-stereospecific, but it is regioselective. So I'm just going to put R for regioselective. Exact same thing over here, non-stereospecific, but it is regioselective. Over here again, plonk on the same side. That's going to be a syn. Over here, it's a syn, and then it gets all scrambled up. The end result doesn't show any stereospecificity. Now, KMnO4, again, syn. If it is cold, you get syn addition. And over here, this is also going to be syn. Ozone actually initially is going to be syn. So you can see a whole bunch of syns here. Uh-oh, it's too bad now, but we've already committed them. So let's see what we can do with these molecules and reagents. If you did a small little modification to your initial starting material, are they all going to be enantiomers? What's going to happen if you change this a little bit? Let's do it.